Okay, now I just do a little bit of recap about our lecture last time. We started from the Coulomb's law. This is from one charge as the source and one charge as the test. And you can imagine that this is the generator of all the electric forces, and you are holding the charge for the test, the Q test, and you are doing the measurement. You measure the strength of the force between the two charges. So you can apply the simplest Coulomb's law. So here are the two charges, and this is the distance between the two charges, and here is something showing you the direction of your force. And now we can think about the strength of the force. It only depends on the distance between the two charges. So actually we can do kind of generalization like this. So we can treat the Q0, the only Q, we just treat it as a source of a distribution of forces. In this case, the distribution is radial. So this is the nature of electric force. And we just find that the amount of your test charge, the Q test, is just a constant. It's just a scaling factor. So if we focus on the distribution and the shape of the electric field, the number of Q tests is not really relevant. The only important thing is the strength from the source charge and the distance right here. So that this kind of thinking mindset leading us to a concept. This is the electric field, and this is the definition of electric field. So this is the number of charges from the sources. This is how far you are from the sources, and this is just showing you the direction of your electric field. And the symbol right here is just in capital E with a vector. And when you look at the words electric field, then you can always think of a distribution of forces in a two-dimensional place or in three-dimensional place. And then we are coming to a important thing, but it gets a little bit more tricky. Now we are interested in the electric field generated by many particles. So here are three charges, and actually this is simple, but it's just technically troublesome. The simplest thing is the summation of the electric field on your test point is just the superposition of individual electric fields. So you just calculate the electric field from Q1 to Q3 like this. You have three electric fields. Oh no, this one. You have three electric fields, and you just superposition them. You just add them up together. They can be added up linearly. So this is simple. And the charges for your test is just a scale for the force. So you can calculate the electric field like this first. And if you want to know the force, then you just multiply everything by the Q test. So this is simple. And this is for three charges, and if you have n charges, no, the index is I. So if you have many charges and the number of the charges is I, we just put labels on them, and we just apply the same superposition principle. And if the distribution is continuous, then we can change the symbol a little bit. Then we can apply the principles of integration. So the important thing is now we are dividing your distribution into small pieces, and every pieces have a little portion of the charge, and we put the index on it. This is I. So this is 1, 2, 3, 4, 2, I. And we just take each little piece of the charge. We measure the distance between the charge and your test point. So this is the absolute value of your vector. But this is from the point I, for example, the point I to your test point. So this is just the distance between them. It's labeled the vector Ri, and this is the absolute value. And this is the unit vector showing you the direction like this. Yeah, so this is the electric field generated by each little pieces of the charge, and the superposition is done like this. So now we just make the symbol a little bit simplified. So the index I here, we don't need it anymore. Then this R, we can just take it as a scalar, R squared. This is from Coulomb's law. And the little portion of the charges, then this is the little unit of the charges that need to be integrated. And this is the direction. Though you just see a hat R right here, then the decomposition depends on your coordinate system. Now the coordinate system is Cartesian, so we have x-axis and y-axis. So actually the vector R here should be written as a addition of something hat x, something hat y. They should be decomposed in a form like that, and then you do the operation on x first, y, and then you recompose them. So it's just the same principle for all the vector analysis. 这边可能大家容易突然之间忘记的部分，我再提醒大家一下。这边有一个方向的单位向量，那你的单位向量它实质上是什么东西？就它细节上是什么东西？是依照你的坐标系统而定的。像我们现在的坐标系统是笛卡尔坐标系统，就是正的跟有一个 x 跟一个 y 轴。那其实你的 hat r， 你实际上在操作的时候，你要把它分解成 x 轴上的分量 ，y 轴上面的分量，你两边分别处理完之后，你再把 x 跟 y， 你再把它 recompose 起来。对，所以这是实际上操作的事情。那我们在数学上面，你就写一个 hat r， 因为它看起来比较清爽，比较干净。好，那么这是一般向量操作的原则，这个原则是不会改变的。那么再来是，如果说你把电场算出来，所谓的电场就是我们先处理 source 的问题。你 source 的问题你先处理好之后呢，如果你还想要知道，那我实际上的力那个到底几牛顿的时候，你再把你的 test charge 乘上你的电场，然后那个数字就是一模一样。对，好，所以这是我们一般在做电场分析的时候的操作方法。OK。And this is the definition, and I just showed you some typical geometries for electric field. We are very interested in the electric field created by these different geometries, and then we just went through the calculation for the stick last time. Sorry, I have to update because some students asked me some questions and I just realized that I need to do a little bit more explanations. So I updated my slide yesterday. Wait a second. 因为有一些同学上次问了我觉得很重要的问题，所以我重新做了一些投影片。想弄得更清楚一点，因为像我自己是因为这些什么高斯定律、什么定律我已经用得很熟了，所以我常会忘记有一些点其实是很重要。好，上次我觉得有些同学问了非常关键的问题。So last time, just after the lecture, some students asked me some crucial questions. So the question is, here is the definition for in the framework of integration, and we are treating every little pieces of the charges like this, and we want to calculate the electric field from every little piece of the charge. And now we have two parameters, two changing parameters in the equations, right? So one of them, the Q, it might be changing on different position of your distribution. And the other changing parameter is the distance R, distance between the test charge and the source charge. So this is R. And when we are doing the integration, how do we decide which one we are doing the integration? So 这个问题我用中文再讲一遍。上次有同学就问说，好，我用库伦定律把每一小坨电荷产生的电场写下来了，长这样没错。可是老师，你看哦，这个电荷它是会随着位置不一样，它是会变的，对吧？然后这边有一个距离，就是电荷到我测试点之间的距离。那我在做积分从头扫到尾的时候，它也是会变的，不是吗？那我们现在有一个 charge 是会变的，有一个 r 是会变的。那我怎么知道我积分的时候我在积谁啊？所以那时候有连续几个同学都问了同样的问题，那么这就是回答哦。So actually the point here is we are always trying to turn the distribution of your charges into a function of position. 这个用英文讲应该没人听懂，就是那我们现在的问题就是在于处理这件事情的技巧了。那它的技巧就是你要想办法把电荷的分布转换成一个位置的方程式。就是你现在知道电荷嘛，然后你可能知道在不同的位置上面电荷的数字会改变，但是没有关系，你只要知道你的电荷跟位置之间的关系。像我们这边是非常简化的版本，我们就直接假设电荷的分布在整条棍子上面都是均匀的，那么你就可以把电荷的这个数字，你可以把它转换成线密度乘上一个位置的函数。然后呢，你整条方程式里面唯一的变数就是位置，就是 geometry 了。那这样子你就把这两个参数会不同步的问题你就解掉了。所以这是我们在处理电场问题的时候一个我觉得很关键的点。对，就是你大部分的人啊，我们这都是在各种尝试跟错误里面去找到一个适当的方法，把电荷的部分转换成一个位置的函数。然后你就可以只处理位置的问题就好，你只要处理位置的向量就好。所以就是你们还蛮厉害的，看会发现说这件事情怪怪的，但是没错，这就是接下来解题的关键。我看一下，这也是为什么我们在 and this is the reason why last lecture I just show you the slide like this. So the simplest strategy to solve this problem is like we just treat the charges as homogeneously distributed, and then we can turn the number of the charges into an equation of volume, area, and length. And here's just the density. This is a constant everywhere. And when you're doing the integrations, then you can just focus on the geometries of the volume, the area, and the length. And this is just correlated with your distance. 这就是为什么上次要给大家一个定义，就是密度。对，因为我们通常我们在处理这些事情的时候，电荷我们都会我们先处理均匀分布的问题啦，以后我们再来处理不均匀的问题。我们先从比较简单的均匀分布的开始。那这时候比较简单的就是你可以把电荷的数量，你可以把它转换成它是密度乘上一个体积、一个面积或是一个长度。那这个体积、面积、长度，然后你就可以再转换成 x 跟 y 的加减乘除。那这样子，你把它放到你的库伦定律里面来的时候呢，这一团它就会变成某一个密度常数，密度常数你就可以丢出去。然后呢，这边就是位置就跟你的几何形状有关系，再来这边就会变成体积、面积或常数，也是跟你的几何形状有关系。所以你的整个问题就简化成说，我们是在处理那个几何形状积分的问题了。好 ，OK。And this is And this is how we treat a stick. And I just give you a clear explanation here, but you can check the procedure of derivation by yourself later. And the trick we are applying here is let's fix the charge first. So the charge here, we can turn it into the line density multiplied by the length of a little unit for your integration. So this is lambda dx. And now we are standing right here. The distance between the charge and yourself is always on the x-axis. So the distance here turns into x. And the vector here is always hat x. And this is how you do it in a very simple way, but you just change a lot of parameters into a function of x. So k, e is constant, lambda is constant, this is x, and this is x, this is the direction of x. Then you can make it very simple. And I think from this case, you can also see one thing. So when you're doing the integration for electric field, the choice of your coordinate system is very important. 就是你应该也会注意到一件事情，就是你在处理电场的问题的时候，选择坐标系统是很重要的一环。就是你的坐标系统的原点跟它的轴你要放对方向，你的积分就会变得很简单。它通常判断的原则用一根棍子应该看不出来，但是你之后就会慢慢发现，就是你如果把你的坐标系统的原点放在对称轴上面，或是旋转对称轴的轴心上面，通常你所有的操作就会变得很简单。Okay, so this is the importance of choosing your coordinate system. Yeah. Okay, let's do recording. And here's the procedure of the calculation, so you can just go through it by yourself. When you get the important principles, and then these are just techniques. And today we are working on a ring. So, before we start all the derivations, let's just look at the ring and look at the configuration, and let's do a little bit of analysis on it. So this is a conducting ring, and here are electric charges evenly distributed on it. We just cut the ring into small pieces, and the charge on each small pieces is dq. And this is the center of the ring. This is where your charge is. And this is A, the diameter of the ring. And this is a circular ring, so when you walk on the ring, and all the A are the same. So A is a constant here. And this is the axis of X. We are standing right here. And we are measuring the direction and the strength of your electric force. So let's just pick one piece of your ring. This is dq, and the dE here, this one, this is the electric field created by the dq here. And originally the direction is pointing like this. And for our analysis, we decompose the dE into two components. One component is on the x-axis on the same direction as the x-axis. So this is a projection of the dE onto your working axis. And the other component is this one, the component which is perpendicular to your working axis. So we do the decomposition like this before we do a lot of calculation, because it makes it easier. And now you can think about one thing. If you walk on the ring from here to here, and you just add all of the dE from each component up, and the thing is going to happen is like this. the projection on the x-axis, they always add up, and it gets bigger and bigger and bigger. But the component perpendicular to your axis is just like rotating like this, isn't it? Can you imagine it? So here is a typical case. So the detail here, it creates D, E perpendicular to this direction downwards. But if you look at this one, if you take these little pieces and you create a DE like this, and the projection on the x-axis is exactly the same, but the E perpendicular is pointing to this direction with the same strength but opposite direction, so they just cancel out and they disappear. So you can see that in a symmetric, rotationally symmetric geometry like this, only the electric field on your working axis really matters. But the other one, this one, they cancel out anyway if you integrate over the loop. So you don't need to be scared by the complicated geometry. If you can find kind of symmetry in it, and then they always cancel out. 好，这边重点部分我用中文再讲一次。你可以注意一下哦，就是如果你只切一小块电荷，然后呢，你知道它产生的电场是橘色这根像这样往这边这样指过来。但是如果你看它正对面的这一块，对不起，你也切一小块下来，然后这一小块电荷它产生的电场是这样指过去，然后它们这个角度它会是一样的。那你如果把这一个DE往你的工作轴，就是 x 轴上面投影，你会发现DEX 这个 component 是一模一样的。然后呢，这个 D， 然后垂直呢，它是往这里指过去，而且这根跟这根它们的强度是一模一样的，只是它们指向相反的方向。好，然后呢，这边是一个圆圈嘛，那假设你顺着圆圈一直走，然后它每一个 little pieces 它产生的 component 都会产生一样的抵消的效果，所以其实你一看到这样子，你会觉得很害怕，哇塞，这什么东西啊？但是你稍微看一下它的对称性之后，你就会发现，没有啊，不用害怕，我只要管在 x 轴上面的分量就好了，因为垂直于 x 轴的分量，它们无论如何都会因为抵消而消失，这个是对称性产生的效果。所以你以后在处理电场的问题的时候，你安装你的工作轴嘛，你把它装上去，你只要找到一个对称性，然后把轴放对的地方，你的问题都会变得很简单。好，所以这是我们在开始之前的一点小小的分析。通常你在开始工作以前，如果你先静下心来看清楚，然后你就可以不需要使用暴力解法。好，这就是那么我们接下来分析了一大堆，我们现在要把符号放进去了。So we just did the analysis, and now we are assigning symbols, the correct symbols, into our equations. So first, again, we start from the Coulomb's law for the electric field. And in this case, the dq is just dq. It's evenly distributed. And now the distance r is... but now we have to think about one thing. So the dE here, it should be the projection of the original dE on the x-axis. So that's why we have a cosine theta here. So this is for the projection. The projection from the orange one to the light orange one. And this is done by the cosine theta here. The theta is this one, and the theta is equal to this angle. That's the reason why. Okay, and here, let's look at the green boxes. This is for the distance r squared. So r is from here to here. And this is a squared plus x squared. So from this one to this one. I'm going to each step very detailed. Yeah. So it could be a little bit slow. But I hope every step is clear enough. And for the cosine theta, we rely on the geometry again. So now the cosine theta is x divided by r, this one. And then you use the same equation to turn r into a function of x. And the cosine theta is just, we're going to put this one into here. You can just look at the color of the boxes and you can track the steps. Okay, seems like everyone is following, and now we are going here. So let's do a little bit of arrangement for the equations. So here we see the big structure from the Coulomb's law, and this is from cosine theta from the geometry. It looks a little bit complicated, but we can just try to put them together. So now the a squared, x squared, you can just combine them, and this is this one, and with the power 3 over 2. Kex dq, and it should be okay. Then we do the integration. So this is integrate. We just integrate everything, and the integration here is you are summing up all the small pieces on the ring. But let's take a look at it. So now when we are doing the summation over the ring, you're standing here, you're not moving around, right? So the x is a constant. The diameter, a, is another constant. It's not changing when you are integrating. Not changing, not changing. The only thing which change is the number of the charges on the ring. So it looks very terrible at the beginning, but if you just calm down, chill, and think about it, you can see that actually the x and the a doesn't matter at all when you're doing the integration. It's another magic done by the symmetry. So you see all the constants with x and a, they are geometrical factors. And the part from the q is from the charge. 所以你就会发现哦，在这一整条公式里面有一大坨，那个是这是几何形状造成的效果。然后呢，这是电荷实际上产生电力的部分。你可以把它切割成两个部分来看，一部分是几何形状，另外一部分是电荷。然后这个整个过程，大家可以稍微注意一下。就是你在你顺着这条圆圈走一圈，你会发现，因为你测量的点都没有改变，都是在原来的位置并没有动，所以其实你的 a 是常数，你的 x 也是常数。那么你在做积分的时候，这一大坨看起来超可怕，可是其实它没有任何作用，因为它全部都没有改变嘛，对吧？所以你就可以把它拉出来，然后最后这个问题变得超简单。其实你只要把附着在环上面的电荷到底有几颗，你把它算清楚就好了。所以这就是最后的答案。就是跟高斯定律或是跟库伦定律有关的题目，结果常常都会变成这样，就是你有一部分是跟几何形状产生的一些效果，然后有另外一部分是电荷造成的效果。其实到最后两个部分都会分开处理，它们很少会纠缠在一起。好，所以这是一个 ring。我看一下时间。好，那我们就再继续咯，直接接着马不停蹄，一步一步往下。好，那我们现在要再继续往前进，我们要来处理圆盘的事情了。Then we continue with the circular plate. So how you look at this problem? You can treat the circular plate as rings and rings and rings and rings. That means you can just cut it into a small ring, a middle ring, and a bigger and bigger one, and then you just cut them into rings, and then you just put them together. You just stack them one by one, and you can construct a plate from a lot of rings. And this is what we calculated. This is the electric field from one ring. It depends on the radius of the ring. This is the A. It depends on your distance from your plate. So this is X. And it depends on the number of charges attached on the ring. And then we go on for the plate. Now we just treat the dq first. So now we are treating the plate, so we focus on the area density. This is the unit area for your integration. And here's one thing, the unit area here we calculated in polar coordinates. So in polar coordinates, the unit area is defined this way. Here are some theory, mathematical theory behind it, so you can check the textbook for calculus. I'm sure they are showing you why a unit vector, or why a unit area for integration is this, but you can imagine it in your head. This is 2 pi r dr. 2 pi r is the length of your circle, and dr is the distance, like this one here. The distance right here is dr, and if you multiply your dr with the length of your circle, then you get the area. 这部分是大家常常会想说，真的吗？不对吧？因为我内圈跟外圈的圆周不一样吗？为什么这样算出来的面积是可以这样用吗？大部分人都会问这个问题。那大家可以去看一下那个微积分里面的书，它里面我记得应该有一章节，它会推导，然后它会跟你证明说为什么这件事情在微积分的状况下是行得通的。就大家可以看一下你们微积分的课本。Okay. So this is how you treat the distribution of your charge. Then we need to modify our equations a little bit. Now the electric field for one ring turns into a little portion of the electric field. And now the a squared is the radius. So we are changing the a into r. R is from 0 to the radius of the plate. And the q here is turning into a unit of charges to be integrated. Then the dq is replaced by the 2 pi r sigma r dr. This one here. 好，我们现在要做一点改装。所以这是一条环，就是一个环产生的电场。那我们把这一个环产生的电场当成是一个小单位的电场。那我们现在对圆盘要做的事情，就是把这每一个环产生的电场，你要用积分把它积起来，把它积成一个环。那你现在稍微改装一下，我们的环的直径 A， 现在我们把它换成 r。然后 r 的变化是从圆心开始的0，一直到你的圆盘的半径。所以这是我们等下积分的时候我们要动手脚的地方。那么再来呢是这里，我们要把 dq 把它换成2 pi sigma r dr， 这是我们前面推导出来的。好，然后 x 的部分没有改变 ，x 就是你跟你自己本人测量的人跟圆盘之间的距离 ，x 的部分不需要改变。好，所以我们动一点小手脚，我们再来继续。那我们这边开始来做积分。So now we just change the parameters and now we start to do the integration. The integration is along your plate from the center to the edge. And at the center, your r is 0. And on the edge of your plate, your r is the capital R. you're integrating from 0 to r. The variable is the diameter, r. So this is the equation that you need to integrate. And now we're doing another technique. So this 2r dr, actually, you can turn it into another equation. So this is the derivative on r squared. Because if you do a derivative on your r squared, then you get 2r, and the dr squared is just equal to 2r dr. So you can change this one into the derivative on the r squared. So now you have a r squared, this is another r squared, then the integration is getting easier. 所以这边是另外一个技巧，它跟物理没有关系。对，但是你会这一步的话，你就做起来比较顺。你可以看这边有一个2r dr， 其实你可以透过一些微积分之间的关系，我就不念过去了，你自己看。就你可以透过一些微积分之间的关系，你可以把2r dr 撤换成 d， 然后 r squared。然后你这样做的好处就是，在这条公式里面有一个 r 平方，你这里有个 dr 平方，然后你在做积分的时候比较容易，你就不会那边鬼打架了，就是你就不会这边 r 平方，还有3×2，然后 power， 你就一堆很痛苦，那你会用这些小技巧，然后你可以把你的 integration 简化，所以这是你积分后的结果。最后就是这大坨把大 R 带进去，这大坨把0带进去相减，然后所以这就是你最后得到的结果。Okay, and we get the equation, and now we are doing an analysis on the approximation. So now, usually the important thing is, if we have a situation like r at the x is much smaller than r, the capital R. This is the case when you are walking to your plate and you are standing very close to your plate. And relatively, you can say that your plate is very big compared to the distance that you are between you and your plate. So if the x is much smaller than r, this is negligible, and this is very big. Then you can do a little, this is small, this is big. So this one is going to be very close to 0. And finally, which matter is the 2 pi k sigma. This one, only this one matter. This term doesn't matter at all. And you have a sigma divided by 2 epsilon 0 because the Coulomb's constant is this one, the fundamental expression. So now you can see that when you're very close to your plate, when your plate is very big, practically what you feel is a electric field, a evenly distributed electric field, and this is just the evenly distributed charge. 所以这边我们通常会这样子啦，就是你算出来一个公式，如果说很大包、很复杂、term 很多的话，那么你通常会做一点极端值的近似，然后你去检查一下你算出来的结果合不合理，所以这是一个很重要的检查步骤。那对于我们的 plane 来讲，我们的检查方式就是呢，你假设你的 x 非常的小，然后你的 r 非常的大，它的状况就是你站在这里，你在测量电场的时候，你离你的圆盘很近，所以相对来讲，你就会觉得你的圆盘超大，非常的大，大到看不到尽头。这时候呢，你可以想象你会看到什么东西？这时候你看到的圆盘应该很接近一个巨大的平板吧？然后呢，你不管原本电场的形状是怎么样， 你都会感觉你的电场好像是平行于你的电板，然后垂直的冒出来，对吧？而且你应该会觉得那个电场很均匀。那我们现在来推测一下，看你刚才推导出来的公式能不能够产生这样子的效果？答案是可以，因为你的 x 很小的时候，这个项几乎等于没有，那么你的1就相对起来很大，然后这个项变成很小，你就会发现说，你算出来的 Ex 就是2πke sigma。那你可以把库伦你把库伦常数，你用一个比较 general 的方式，你把它带进去，你就会发现，其实你电场的强度只跟你的电荷分布的密度有关系，这是一个常数。所以呢，好，那你算出来的东西跟在极端的状况底下，跟大家的想象是有 match 到的符合到。So by this kind of check, you can always do a little analysis and see if your result makes sense or not. Make sense, 对。我刚刚就一直很想讲字，但是我找不到。Make sense 就是合不合理的意思。因为通常你做完运算之后，你的公式都会很大一条，就是很复杂。但是你可以用一些极端的状况去检查你算出来的结果到底合不合理。刚刚就帮大家示范了一个检查的方法，检查的原则，大家可以多多利用。OK， 好，哇，好累，休息一下。让我休息一下。好，那我们今天上课的最后30分钟，马不停蹄的我们来讲高斯定律。今天真的讲好多东西，我的妈呀！好，很少进度有这么赶过。好，那我们来看一下，高斯定律这个东西为什么会跑出来 ？So let's check, and that's what happened. Why we need to? How can we derive, and how can we get to the Gauss law? We start from the charge, the point charge, and the radial electric field. So now we are familiar with distribution like this, and we know why it looks like that. And if we have two charges, then what's going to happen? So when you are drawing the electric field lines, and if you have two charges, then the density of your electric field line just double. 就所以，如果你的电荷数量变成原本的2倍的时候，那么我们在图像式的画你的电场线的时候，我们的画法就是把电场线的数量变成2倍。那实际上在做量测的时候，你会量到的东西就是你的电场强度变成原本的2倍。好，那我顺便打个岔，像这种电场线的密度啦、方向的画法是法拉第发明的。那法拉第他会发明这样子的图像式的画法，是因为他不会数学，他是一个只有受过小学教育的人，所以他没有办法用这种东西跟你表达他看到了什么。但是对法拉第而言呢，他可以用画的。对，所以其实我觉得法拉第他很厉害的地方怎么说？就是他的缺陷造就了他的强项。对，然后他的这种图像式的思考方法，他就是一直往前，就会得到一些传承嘛。像我觉得其实费曼应该算是比较近代这种图像式思考的翘楚。我们应该是会到学期末讲费曼图的时候会讲到这件事情。好 ，OK， 所以打个岔，讲个小故事。好，然后呢，这是电荷变成2倍，所以 This is when the charge is doubled. And if the charge is one more time doubled, so now we have 4 portions of the charges, and the electric field strength is 4 times stronger. And if you draw it pictorially, you will have 4 times of numbers of electric field lines. So you can see the scaling between it. can we have a general expression for it? So we can draw it pictorially, and can we try to express, or can we try to describe this kind of situation with some mathematical language? So this is how we do it. First, we have to introduce a concept. This is the electric flux. So you can imagine the electric field lines is pointing, they have a strength, they have a direction, and you can just try to imagine it as flow of water. 你可以先把电场，因为它有一个强度，有一个方向，你可以先，那假设说你现在在里面撒那个电荷的话，电荷就会顺着电场线的方向流过去，这是没有意义的。所以你这是实际上你会观察到的状况。对，那所以你可以想象说，你可以把电场线把它想象成水的流动。And how do you measure things like that? If I have a surface on it, and how much flow is walking through my boundary. So the boundary in this picture is the blue sheet here. And I would like to calculate how much flow is passing through my boundary. So this is the electric field multiplied by the area of my boundary. I define this kind of factor as flux. 所以这是定义哦。我现在定义一个新的参数，我把我的电场乘上它通过的一个边界的面积，就我的电场乘上面积，我把它叫做通量。你可以想象说，你现在有一个水管，你水管这样切一半，它有个截面积，有吗？那你就会去计算说，我现在有多少水从这个截面积里面流过去，这是通量，这是 flux by definition. And this is the simplest case when your electric field line is just perpendicular to your boundary. So the angle between the electric field and the normal vector of your area is 90 degrees. 这边是一个新的定义。那么你要怎么样用向量的方法去处理一个面积这种东西？你最简单的方法就是你现在有一个面积，你把它想象成它是平的，然后呢这边你就定义一个向量，这个向量是垂直于你的边界的表面，垂直哦，所以这件事情很容易搞混，但是这就是垂直。那你现在想要用向量去处理这件事情的话，你就是去观察电场的向量跟面积向量之间的关系。So now we make another definition. We define a vector, a unit vector, just stands vertically on your surface. And if you want to analyze it in the vector analysis framework, then you can just look at the vector of your electric field and look at the vector of your normal vector. This one, the vector A and the vector E. So here's a lot of new things. And then the second case is like this. So I have an electric field, but if my boundary is a little bit tilted, it's not really perpendicular to my electric field. What is a flux? So in this kind of situation, what is the actual amount of electric field lines passing through my surface? Now you can use the vector analysis to calculate it, because the thing is we have to calculate what is the amount of electric field walking through my boundary in a vertical manner. 所以你现在要注意的事情就是，我现在的电场这样穿过去的时候呢，有多少成分是垂直于我的边界穿出去的，有多少成分是平行于我的边界，所以它实际上只是顺着我的边界的表面流走而已，它并没有穿过去。你要把会穿过去的跟不会穿过去的 component 先分开。 So if you have a situation like this, you have to decompose your electric field. They have a component which passes through your boundary vertically, and the other component, which is perpendicular to your surface, is just flowing away. It's not passing through it. So you have to decompose your electric field to two components. And the component which is passing through vertically, this is the electric field and cosine theta. It's just the projection on your unit vector of your area. So this is the angle between the vector A and the electric field. You can see the relation. And the green vector here. So this is E cosine theta. And the E sine theta, this is the component parallel to your surface, which just flows away, which doesn't pass at all. So now you can calculate the flux in this kind of case. So this is the vector E, the inner product, and vector A. And usually it's the vector A confuses everyone. 通常是大家一看到那个 vector， 单位面积的垂直向量 A， 然后你就懵了。通常大家会在这个时候就会很懵。那么解法就是请你要画一个图，没有别的解法。请你在你的公式旁边画一张图，然后你每算一算，你就回去检查一下。对啊，这没有办法。If this is okay, then I am going on. So then the case is like this. If your boundary is sort of elastic, it's not a flat plate anymore. It has kind of curvy structure on it. But since we have the equation in the vector form, we can calculate everything in vector integration now. So actually we are not worried about it at all. So the thing is just the same. We just cut the boundary into small pieces, and every unit pieces of your area is dA in a vector. Now the vector here is the normal vector, this one. And this is just perpendicular to every small pieces of your area. And this is the theta, this is the angle between the normal vector and the flow of your electric field. You can do this to every small pieces on your curvy surface, and you just integrate them. So this is when you're treating geometries with wavy and curvy structure. 那么现在的状况就是，假设你的边界不是一个平板，假设你的边界是有波浪的形状，或是有各种扭曲的形状，那你也不用担心，因为我们已经把它转换成向量形式了。你可以用向量微积分处理这件事情。那它基本的原则是一样的。你就把你的波浪状的边界，你把它剪成小小的一块一块一块，你就先处理每一小块上面的通量是多少，最后你再把它全部加起来。然后也是一样，你可以用向量微积分去处理这个问题。好，到这边还跟得上的话呢，厉害的来了。So let's look at this problem first. So I have an electric field. The electric field is homogeneously distributed, evenly distributed. And I have a box. The box is in 3 dimensions. And what is the number of flux flowing through my box? So the flux is flowing into my box is the electric field strength and the area. And this has a minus sign because it's walking into my box. And on the other side, the amount of flux going out of my box is EdA. And because it's a squared box, it's a cubic box, so the area on the side and the area on the other side is exactly the same. So on this surface and this surface, and all the electric field lines are parallel to my surface and they don't contribute any flux. So the flux is going into my box and going out of my box is just exactly the same, and the summation of them should be 0. 所以如果我有一个均匀的电场，那我现在边界是一个立方体的盒子。那么在盒子的1、2、3、4这4个面，墙壁上面这4个面，我所有的电场都是平行于我盒子的墙壁，所以其实那个电场并没有戳进去，所以它并没有 contribute 任何电的通量进去。那么从从左手边流进去的通量跟右手边流出去的通量是一模一样多的。好，所以这个是在均匀电场，然后还有封闭的边界里面会发生的事情。用一个盒子比较好想。然后 ，What if I have a shell? So I just heard my boss said I just do continuous change of the shapes, which is morphing 变形, and I just change it into a spherical shell. But if you just look at the symmetry and if you look at the geometry, you will find that actually it doesn't change the fact at all. Because, for example, here I have some fluxes flowing through my surface, but only the components which are perpendicular to my surface matter. So only the cosine component matters, but the sine component which is walking through the surface this way, that doesn't matter at all. And if I take the cosine component here and compare it to the cosine component on the other side, you can see that the strength is exactly the same, but it's just the directions are opposite, so they just cancel out. And the same thing happens here and here. So finally, you will find that actually only the if I just do the summation all over my spherical boundary, I will find that actually the flux is 0 again. The flux is going into my boundary and leaving my boundary, and they should be the same. They should be conserved. 然后呢，大家回去可以，这个通常是没有办法一下子就想懂的，所以你回去你可以自己画个图，然后你可以自己思考一下，你就会发现哦，就算我改变我的边界的形状变成一个球体，那么我的通量就是从我的边界左边流进去的量跟右边流出去的量，最后会是一模一样的，所以通量不会突然变多或者突然变少。它的通量的数目一定要是一模一样的，所以这是关于电场跟磁场的一种守恒定律。好 ，and here's another, but this is another case when we need to treat the sources and the drain. 但这就是另外的状况了，像这边是它就是均匀的穿过去嘛，然后我就去分析我的电通量。可是呢，假设说在你的电场里面，你有一个奇异点，意思就是这个奇异点它可能是你的电场的 source， 就是来源，它也有可能是你的电场线全部冲进去的地方，就是排水口 drain。那这种状况的时候呢，那你也是可以用同样的通量的概念去思考这个问题。我们就回到刚才说的，你从一个 pictorial 的图像上面，那你要怎么样去 create 一个数学工具去把你看到的事情描述出来？那这个就是你可以使用的数学工具。你可以去计算哦，就是 this is what you can do with mathematics. So if you see this is a source of stream of electric field. And what we are doing right here is we just create a closed boundary, spherical boundary in polar coordinate system, because this is a radial system. It's easier to work with polar coordinate systems. And I just try to calculate how much is the flux flowing out from a source? And this is the integration that I need to do. And in polar coordinate system, you can see that all of the electric field should be perpendicular to my spherical boundary. So this is very easy, and you can just do the calculation. Yep, this is the electric flux from the source. And here are the calculations that need to be done. So we have the strength of the electric field. It's the same everywhere for point charges. And this is the direction of my electric field. So this is head R. This is on the R direction, going out radially like this. And because we are calculating the electric flux, so we have an inner product, the A, and this is the vector A, this one, which is perpendicular to my surface. And the inner product here always gives us 1. Because cosine 0 is 1. And then you can apply Coulomb's law here. So this is the Coulomb's constant, the number of charges as a source, and this is divided by R2, and the surface, the total surface of your circular boundary is 4 pi r squared. 这是你的球状边界的面积，就是你的那一颗球体的面积，4 pi r 平方。Then you can do some arrangement on it. You see that your flux is always the charge at the center divided by epsilon 0. So this is how you describe the situation in mathematics. So finally, we just get to the Gauss law. So the Gauss law is stating that if you take your electric field, you wrap it up by a closed boundary, then you calculate the flux flowing out of your boundary, you will find that it's always proportional to your number of charges at the center. 所以你就会发现你的高斯定律就跑出来了。它的意思就是呢，我现在有个电场从一坨缩 charge 里面炸出来，然后呢，我用一个封闭的边界把这坨 charge 包起来，然后我去计算有多少电力线从我的封闭边界戳出去。所以呢，你现在计算的东西就是一个表面积分，然后这边有个圈圈，它的意思是你是对一个封闭的表面做一个封闭的积分。然后呢，你这边做的积分，你在做的事情，其实你就是在计算说，从我的封闭边界里面有多少电力线流出去。那你就会发现哦，你这样子算出来的通量，一定是跟你里面的 charge 的数量成正比，就是这是你里面 charge 的数量，这是一个介电系数，然后它是 epsilon 0，是因为我们还在真空里面处理问题。以后如果你的球体里面有灌材料进去的话，那个 epsilon 0就会改变。这就是高斯定律。So this is Gauss law. And the Gauss law is telling us the relation between an electric flux and the charge with an integral equation like this. This is the integration form of Gauss law. It has a derivative form. 这是高斯定律的积分形式。之后会再跟大家介绍高斯定律的微分形式。 Okay, go slow. Okay, so here's just a little summation for you. So if we have a point charge, then you can apply Gauss law this way. This is simple. And if we change the shape of your boundary, but I just try to demonstrate it to you graphically, and then we can see that actually it doesn't change the result. The flux through your boundary is always the same because of the symmetry, you know. 所以你会发现，我们一开始推导的时候是用球壳，用球体，然后呢，但是你如果改变边界的形状的话，其实你最后的结果并不会改变，就是你穿过你的边界，最后产生的那个 flux 其实都会是一样的，不管你怎么计算。那假设说你的边界是 arbitrary 的形状 ，if your boundary has an arbitrary shape, and then you can try to prove it, and you will see that the flux is always the same, it's not changing. And now the only thing which really matters is the number of the source charge inside. And if you have many charges inside, and it's very simple, you just add them up together, and it reflects on the number of the fluxes offset. Okay. So the Gauss law the definition is like this. So this is the flux through any closed surface surrounding a point charge Q is just Q divided by epsilon 0. And this is independent of the shape of that surface. So this is Gauss law. Yeah. So I think this is enough for today.